Okay, perfect. So if you're ready, we'll move to our next speaker. Ben Dong will be talking about learning and learning to solve PDEs. I'm happy to have you here. Please go ahead. Can you unmute yourself, please? We don't hear you. We still don't hear you.
Yeah, can you hear me now?
Yep.
Okay, all right. Sorry about that. So yeah, first I'd like to thank the organizers for putting up this nice workshop, especially during this difficult time. Well, actually, I'm glad that I'm speaking after Chen Xiao, which saved me some some time explaining some of the slides, so I can just quickly go through them. Well, I mainly come from my main research interest in image-related inverse problems. And recently I got interested in PD related inverse problem as well, and they are quite related to each other, and so today I'm going to cover some of the our work that's, well, it's quite some time. It's about 1 or 2 years ago, and I have some new results, so I'll also briefly discuss them. So my talk is basically two parts. The one is on learning PDEs from data, which is inverse problems, and the other is more on solving PDEs when you have a PDE and you want to solve it. And there are a lot of work on on both topics. And I'm gonna present some of the existing work and how we do things differently, and what are potentials of doing it in that way. Okay, and well, this is just a general motivation. Actually, I work in mathematical image processing. When I first saw deep learning, and I was shocked by how well they perform. And at some time, I thought that deep learning was actually almost killed mathematical image processing, but thank God it's not. It didn't happen, but still, it got me really interesting deep learning and how to combine ideas from deep learning with variational or apply harmonic analysis type of approach, for imaging and image processing. But we all know that deep learning, there are still some challenges and theoretical guidance, which is a big thing, and also interpretability and robustness and many other issues. And the perspective that we take, I think everybody in this workshop take is from control perspective, and I don't think I need to convince any of you that why this is a good idea. So I'll just skip to the next part. So this is a general motivation on how we can actually use optimal control to describe, we all know we can use it to describe supervised learning and also reinforced learning. And also meta-learning, we can put them in this generic description where you have your deep network, which is a discrete version of this dynamics. And you have your terminal loss, and you have your running cost. Okay, maybe if you want, you can have some interactions as well, as we saw from Sammy's talk. The control is the parameters that we learn, and they take different forms. When we look at different learning regimes, for example, the control parameter itself is learnable. When we talk about supervised learning, and U takes some specific forms. When we talk about reinforced learning, where it's actually the control, what the treatable parameters is actually in the policy, the agent, where it decides how to act by given the state xt. Okay, and also the meta learning, which is just a parameterization of your parameter. So you can write it as your you're not directly control of U, you control of the parameter theta that controls the the U, and at the end it actually controls the entire dynamics. Okay, so in a way that, well, the model for reinforced learning is a special case of meta learning. And there are many other variants as well. And this is the model part, and then there, well, to solve this, we can use a BP, or you can, or contracted maximum principle. You look at it, from the continuous side and then discretize, and also you can use a dynamic programming, which is, when you solve reinforced learning problem, you mostly, go from dynamic programming, but you can also mix them up. You do not see them very often, because they, for most cases, For example, you do not really use them programming to solve a supervised learning or meta-learning problem. And for most of cases, you don't really use a BP to solve RL unless it's model-based reinforced learning, and the time horizon is not that long, and you probably would use BP to solve it. But anyway, this is just an overview of of the different learning regimes that our group are interested in, and how we can put them together, how we all cast them in this control perspective. And the reason that we really like this is that from this we can see it actually gives us a lot of intuitions how we actually combine traditional modeling philosophies from applied and computational mathematics with deep learning, and we use that for various image-related inverse problems, and also for PD forward, and also the inverse PD problems. Okay, so let's start with with the inverse problem. So what we want to do, actually, what inverse problem, PD-based inverse problem, want to do is to figure out what is the governing principles behind a observed dynamics. Okay, it has application from biology, from meteorology, and also from computer graphics, where people are looking. It's essentially all a model reduction problem. The model is either it's a DNS of Navier-Stokes equation, or the model is entirely unknown. It's in the hand of Mother Nature, and we're trying to figure out a reduced version of it so that it's easy to interpret, and it's computationally efficient to simulate, and so on. I think about a decade ago, people start to use machine learning for inverse problems. I think it started around 2007, and this is a paper in 2009 on Science, where the authors actually use symbolic regression based on evolution computations, to figure out what is the governing equation, what is to identify the system that actually match the observed discrete data. And another group from Microsoft, they also try to figure out the PDEs that are most suitable to process images. Okay, it's in computer vision. And more recently, groups of people, especially Steve Brownton and Nathan Kuss, they've done a lot of wonderful work in this area. And they actually take advantage of sparse regression, or Lassol, or compressed sensing, the idea of compressed sensing, where they form a dictionary that computes necessary atoms, that consists of necessary atoms of the a possible system that we're trying to identify, and also they include numerical approximations of the partial derivatives into the system, and then they use sparse regression to figure out the most concise expression that can best fit the observed data. Okay, so when we look at the literature, and we're thinking there are still some room to improve, especially in the following two aspects. The first one is, can we really go beyond sparse coding framework? That is, can we really go beyond a linear dictionary? What about a nonlinear representation of the unknown response function of the unknown system? Okay, and also, can we actually learn discrete forms of differential operators? And does it help? Well, the first, the objective of going nonlinear or composite nonlinearity is to, for a given computation cost, for a given memory cost, we want the representation to include, to have a bigger model class. Okay, so we know, composite nonlinearity, they're quite efficient. The express power is much better than a linear, wide network. And also the second part, maybe it's not that intuitive, but we're doing inverse problems. Just think that if we do not even know the form or the type of differential equation, how do we know the best way to discretize it? So we think it's best that we estimate the discretization of the differential equation, and also the form of the differential equation at the same time. That means we're actually approximating the forward and also the adjoint of part of the of the problem. So I'll explain later what we mean by that. Okay, and in terms of architecture, it's really just, well, the architecture is really just inspired by numerical differential equations. So if you think that your unknown dynamics can be described by this generic differential equation, and you can do a simple, temporal discretization, for example, for the Euler, you'll get this residual block. And you can discretize these differential operators using, for example, finite difference approximation, and you get a bunch of filters. Okay, they're just convolutions, and you can fit a, at each point you can actually fit a function, and that function is actually shared across all pixels, and that will be your your unknown function f. And the very first version of we call this PDNet, the very first version of it, we have a pretty strong prior knowledge. We need to assume that we know the type of f, and also the maximum possible order. This is a minor assumption, okay? And we can approximate the field, the variable coefficients of, for example, a convection diffusion equation with a nonlinear source. Okay, and later we did another version of it that actually weakening the assumptions on knowing the type of the f, but we still have some assumptions. That is the f. We do not need to assume that this is, for example, convection or diffusion, but this f has to be composed of u and it's the partial derivatives of u. Either by addition or multiplication, or you can throw in division as well. But in our version of, we call this symbolic network that express this f. This is the update that we did, versus the first version of it. And also we need to assume the maximum. So what is this symbolic network? It's actually inspired by work in ICML 2018. We actually have a simplified version of a symbolic network, where this network takes input of the variables u, v, w. For example, we have 3 variables, and also all its partial derivatives. Okay, and then at each, when you deepen this network, we include an operation. It could be multiplication, it could be division, and in our experiments we did multiplication, and so that you can actually express a high order polynomial in terms of u and all its u, v, w and all its partial derivatives. Okay, so that it actually forms a function form, and we do this using regression rather than symbolic regression. So that it's for symbolic regression, the problem is it doesn't really scale well. And also when we added more constraints, and to make this, to stabilize the training, these are actually quite important. We add a sparsity constraint. We also add a pseudo upwind as a constraint. So if you do all that, we're still not able to identify the equations, because if you learn filters to describe a observed dynamics, those filters are not guaranteed to be approximation of differential operators. So actually, it's actually motivated by our earlier work, where we find the connection between wavelets and the differential operators. We can actually prove in wavelet with certain vanishing moments, actually approximation of differential operators in the pretty generic setting. Okay, in the weak form, and in terms of filters, wavelet filters with certain sum rules or discrete vanishing moments actually connects with the differential operators, or the finite difference approximation of differential operators. So for given any filter Q, we can construct a matrix M. We call it moment matrix, which basically, this is actually the terms from Taylor expansion. It's very simple calculus. Okay, but with that, this is a linear transformation from Q to M. And then we can actually put constraint on M so that we can approximate any differential operators, okay? And for example, if you want to approximate partial X, and this will be the moment, the constraint that you put on the moment matrix M. And if you want the filters to be learnable, okay, we found that this is particularly helpful, for inverse problems. Okay, you can actually let go these 3, constraints. You only constrain part of the moment matrix, and you can, increase the degree of freedom. And we found these 2 type of approaches are actually quite helpful. It actually ensures that we know which filters actually approximate which differential operators, and also it gives enough flexibilities in finding the best scheme to approximate the differential operators to help solve the inverse problem, not the forward problem, but the inverse problem. Okay, so we did elliptic experiments, and we generate the data by using the Berger's equation and adding noise, but we do not assume that we know it's Berger. Okay, and we use actually 3-layer, I think a 3-layer or 4-layer a symbolic network, which is pretty. It can represent very complicated expressions, and this is the system that we identified, plus the remaining terms that are actually shown in here. Okay, these are actually pretty small remaining terms. And what's interesting in here is that if we actually assume that we know it's Berger's and we choose a discrete method that is actually stable for Berger's, it actually make the system identification worse than learning the approximation. This actually this actually supports our initial motivations that we want to learn the discretizations while we're actually solving the inverse problem. I think it's a new observation that when you solve the inverse problem, you need to learn adaptively, find a way to solve the forward problem so that you can identify the system better. And this is actually an example that is indeed learning the discrete forms of the different of the differential equation actually helps with the inverse problem. Okay, and these are actually the comparison between frozen and the actual PD nets in terms of the prediction. Once you fit the model and you can just generate random initialization, then you can pass it through the system and it can make accurate predictions. Okay, and this is just another more complicated example. Okay, this is actually one of our recent work. It's actually motivated by a project. It's an industrial project, and what they want us to do is they have a system, and it's with quite a few variables, and and they have a few observations. They want us to figure out what is the functional dependence. It's a dynamic system. They want to figure out the dependence of these variables as a differential equation. But for any given system, they only have very few observations because practical limitations. But what they can do is they can actually give observations of multiple different systems. So we actually model this as a random as the inverse problem for random ordinary differential equation. That means for each given system, it's an instance, it's a realization, it's a sampling from a random system that is an ODE with coefficients that are random variables. Okay, and so that we can we fit the system, and so that it can better describe all those systems, and so that we can actually figure out what is the governing equation behind all that. Okay, because we believe that for different machines, the principles are the same, but it's actually the realizations are slightly different. Okay, so we cast this as finding from the data, from all of this data, we want to figure out what is the formula F. Actually, what we essentially want to do is figure out the support of this distribution P and also the expression of this distribution P on that support. Okay, so let me just quickly skip through. Well, basically, we just combine the symbolic net. We call it OD net, which is because we do not have partial derivatives, so we just throw away the partial derivatives and using the symbolic network. And also at the same time, we use GAN to fit the distribution of the random of eta. Actually, it's the samples of this eta sub I. Okay, and we actually train this alternatively. So basically, we are trying to minimize this joint loss function. Okay, so we use GAN to describe, to fit the random variables, and then we use the OD nets to fit the data. Okay, and I won't go into details. If you're interested, we put this paper on arXiv, and you can see more details on that. Okay, so let me jump to the second topic. I think I only have 5 minutes. So solving differential equations, and there has been a lot of work, and there are mainly two ways of using neural networks to solve differential equations. One is to use neural networks as an ansatz to replace the variable u. For example, the PDE has variable u, and you use u sub theta, where u sub theta is a neural network. Okay, you use it as an ansatz to approximate the solution, or you use neural networks to approximate the mapping to find the solutions. Okay, that is mapping from your initial and boundary condition to the solution and use a neural network to approximate this mapping. And maybe there are many two different approaches. They each of them have their pros and cons. What we did in this work, it's jointly with a few of my students, is the mapping. It is the second part. Okay. So what we do is we look at we experiment on 1D scalar conservation laws, and we look at the one of the benchmark numerical schemes of Wino, and we regard this iterative scheme as a dynamics. Actually, to be more precise, we want to regard this as a Markov decision process. It's just for Wino, the decision has already been made by human. But we want to improve that, especially we know for Wino, it does a great job. It's optimal. You can prove it's optimal in smooth regions, but it's actually using near singularities, which is a more conservative way of choosing the stencils. So we want to see whether we can use machine learning. Actually, we want to use reinforced learning to try to improve that. Okay, so the key here is to form a MDP, and basically, the key is to define. For MDP, the key element for it is the state, the action, and also the reward function. The transition is automatic because we have this update scheme for that. But we need to define what is state and what is action and what is the reward. And what we did is that the state is the current approximation of the numerical flux, and also the row speed. Well, actually, including the row speed is very important. Without that, it's really hard to learn a stable approximation. But this actually shows that we have to combine machine learning with our prior knowledge. You cannot just feed a black box neural network and hope it works well. I don't think it works very well in general. And also the action is we use a policy network to determine the weights of the stencils. We're hoping that they can do something differently. Particularly at the singularities, okay, and also this is the state transition, okay. So and we use the local infinity norm as the reward, and so that it can suppress oscillations. So this is something that we do not want to see, and we train it on the specific flux, and also on the Euler discretization of the in time, and also. I think RK2, I think, no, it's just, yeah, for Euler in time, and also with Wino 5. And this is the spatial temporal discretization, and so this is terminal time, okay? And we actually tested for other settings, and it's, other than this circle setting in red, we actually tested in all of the other settings actual generalization. We found that using reinforced learning generalizes particularly well. The reason is that at the very beginning, I said that reinforced learning is the model itself. If you look at the dynamics, it's a special case of meta learning, and we know meta learning, it's generalized pretty well. They actually, people use meta learning just to to handle part of the reason they introduce meta learning is to handle the generalization issue. And that's that's a heuristic explanation why this actually generalized pretty well. This is the overall accuracy, well, error. This is actually overall error, and it's comparable with Wino. And it's actually also generalized to other fluxes, but it does not have very good generalization to wild fluxes. For example, if you use a non-convex flux, it does not work that well, but it has a mild generalization ability to other fluxes. And it particularly does better than we know at near singularities. This is actually what we're hoping to see. And this is just two examples at the certain singularities. And we also did a statistics to see how, just because this is a spatial temporal, and we can give you some examples where it does good, but how it does, this is the accumulated error. So how to read this? Okay, so the horizontal line is the error, and the vertical line is actually the number of voxels in the spatial temporal grid that achieves that arrow. So basically, the curves, if the curve is more on the left, it's better. Okay, so in smooth regions, the reinforced learning, the RL we know doesn't really do better than we know. Okay, this is what we expect because we know 5 is optimal. But near singularities, okay, it's you can see that even though this is not doesn't look that significant, but it's statistically you can see that it is better than than we know. And also another particular interesting part is that we also look at the stencils that reinforced learning chooses versus the stencils that we know computes. Well, the ones on top is the RL selected weights, and the one on the bottom is the we know selected weights. And what you can see that, for example, over here, the we know selects weights that is more on the left side. Okay, it's more conservative way of selecting weights. But RL seems it selects a more aggressive weights. So we cannot explain why it does it. And we haven't really get a chance to see how often it actually does this, but it's actually sort of interesting that it does things differently, near singularities, and also for this type of near around singularity, or at least for this type of time instance, it's just the relative L2 error of R we know is significantly better than we know. Okay, so. All right, so let me just quickly, summarize this. The reason that, well, many people ask me why we use reinforced learning rather than supervised learning, and I think they ask a fair question because reinforced learning is really, really hard to train, and we're having trouble to extend this to 2D and 3D. It's really time consuming. But we do see the benefit of it. I think the major benefit is that if you use reinforced learning to design a policy that gives you that decide on how to approximate solution locally, and this decision is made non-greedy. It actually considers long-term accuracy rather than it try to approximate the current time step in the best way. So the non-greedy, I think, is the major advantage of using reinforced learning. But of course, you can use supervised learning to achieve non-greediness. But you have to use BP to train a network that is really, really deep. For example, it's maybe 100 or maybe 1,000, and using a reinforced learning to train it, I think it has its own benefit. And before I end, I just this is another work that I think is very interesting, that we use reinforced learning to achieve personalized scanning for CT imaging. We know normally for CT imaging, the angles and the dose are actually selected, and for basically for different patients, it's pretty much the same. So what if we want we use reinforced learning to adaptively choose the desirable number of and also the specific angles to scan, and also the dose at each given angle, and so that we can actually either minimize the total dose or make sure that the total dose is restricted in a certain amount, and also we want to maximize the imaging quality. So we actually this is actually a combinatoric. So for selected angle, this is a combinatoric optimization problem. And for those, is a continuum variable. It's actually coupled together. We actually use reinforced learning to do that. And it's if you compare with the random with the random angle and a selection and equal dose and the dynamic sampling and also reinforced learning, you can see clear advantage of the sampling strategy using reinforced learning. And also it indeed presents a personalized scanning, because on the APM data set, the test set has 350 images, and it's the number of angles that the RL actually selected. It ranges from 45 to 64, and they choose 45 for images that are relatively simple, and they choose 64 angles for the images that are relatively complex. And also the dose allocations are actually different. But if the number of angles are actually similar to each other, the dose allocations are actually similar to each other. Okay, and you actually when you train the RL agent using a quick reconstructor, and you can actually generalize to other reconstructor, and it doesn't care the image reconstruction algorithm, whether it's a traditional algorithm, or it's a wavelet, or it's a TV, or it's a primordial. This is a primordial network. It's a deep network. You get consistently improvement in terms of image quality. So that means you can really use this personalized scanning strategy realized by reinforcement learning to improve image reconstruction. You can use them together with your favorite reconstructor. Okay, so let me stop here. Just there are other, there are a lot of future directions that we would want to explore, but I think I'm running out of time, so I'll just stop here and I'll take questions if I still have time to.
Okay, great. Thank you very much. That was an interesting talk. Maybe we can switch the screen already to our last speaker. If there's a super quick question, we can do it now. Otherwise, we're here after the session also.